Pritish Yuvraj, and welcome to my channel Design and Analysis of Algorithms. In the previous lecture, we read about time complexity and asymptotic notations. In this lecture, we'll study about Master Theorem and how to apply it. In the subsequent class, we'll learn about the proof of Master Theorem. So without further delay, let's start with Master Theorem. The theorem is applicable only for cases when you have to compute time complexity for a recursive function. For iterative functions, in the last class you saw how easy it is to calculate the time complexity. Look at the for loops, look at the while loops, constants, and you can easily make out it's n squared, it's n cubed, etc., etc. But for recursive algorithms, it's not that straightforward, and hence we require Master Theorem. But a word of caution: not all algorithms, or not all recursive algorithms, can be computed using Master Theorem. If an algorithm is not being able to compute using Master Theorem, you have to move to techniques such as substitution and normal elongation of the tree structure, which is created by the recursive function. First of all, Master Theorem. Any recursive function can be written in this particular form. T of n, the function, is equal to a t n b plus fn. This a here means the number of different a single function creating number of branches. Right. So this a stands for that number of branches, and in the subsequent lecture I'll give an in-depth view of what a and b looks like. But for now, let's just remember that this b stands for how many times or how are you dividing the array in a recursive function. For example, in sorting algorithm, you might divide the array into two halves at each step. So dividing into two halves the entire array, that is b, and because you divided the array into two halves, now you have two new fresh arrays. That is a, the constant a. So a stands for number of arrays being created, and b stands for the size of the array of partitioned by. And this fn means the normal computation. So after you have divided the array into two halves or three halves or four halves, what operation you do on that particular step, that is fn. And Master Theorem is in a very straightforward terms, in terms of layman, it's a comparison at each and every step which particular one dominates. Is it the division process that dominates, or it's the amount of calculations you do at one particular step that dominates, which again we'll see in more depth in the subsequent lecture. But first this one. So a t n by b plus fn. If, and this is how we compare both the sides, fn, the constant which the operations which happen at one single level, we compare that with n, size of the array, log a b. So in case 1, a minus epsilon, there's some epsilon constant greater than 1 or 0, which we subtract from a. What we are doing here is comparing these two functions. If this side is slightly greater than this side, we say that this particular part of the algorithm will have the dominance, and no matter what is the complexity of the fn part, this part will dominate, and the time complexity will be judged because of this particular half. In second case, we see that these two are actually equal. Fn is equal to theta of n log ab. Fn is equal to theta of n log ab, which means that both of them are comparable. In that case, we go to the case 2 of Master Theorem, where we take n log a and b plus log n. And this is the case where this is how we solve most of the merging algorithms, or like when searching, for example. I'll come to this later. And the third part is fn is equal to omega of n log a plus e by b. This case means that fn has the precedence over this particular half. So in a recursive function at one particular level, this particular side is having the dominance. It's much more expensive to compute fn compared to this half, so it takes precedence, and hence you see theta of fn. So if you see the pattern, the first one, when this part has the dominance, it's n log ab. When both are equal, it's n log ab log n. And when this half has the dominance, it's theta of fn in very simple terms. Now we'll look at some examples of solving some questions of recursive, and we'll solve them using recursive Master Theorem in this one. Let's start with these two simple algorithms, these two simple cases where we try and use Master Theorem to solve them. So in the first case, you can see that A is equal to 9, this one, and B is equal to 3, this one. Fn is equal to n, right? Now let's go to the transformation. So it's n log of A by B, which is n log of 9 by 3, which is n log 3 squared 3, or n squared log 3, which is 1, n squared. So on the left side, this part is n squared. On the right side is n. Clearly, n squared is polynomially greater than n. Hence, this side dominates, and the runtime for the entire recursive algorithm is n log ab, which is n squared. So irrespective of how much computation happens at each step, this one, the division of the tree, dominates, and we get n squared algorithm. Case 2. Here, a is equal to 1. There's no a over here. B is equal to 3 by 2. You have to flip this one to take b. And then fn is equal to n power 0, or which is 1, fn. Here, when we transform it, n log a b, n log 1, 3 by 2, right? Anything with this 1 in log is 0, so it's n power 0, which is 1. Now this is a situation where on the left side it's a constant 1, on the right side it's a constant 1. So we apply the second case of Master Theorem, which is nothing but n log ab ln n. So we know that n log ab, this one, is 1. So it's 1 ln n. So the runtime for this algorithm is ln n. Let's look at two more examples. So in this example, a is 3, b is 4, and fn is n log n, right? So transforming a and b, it's n log 3 by 4, and this side is n log n. Clearly, n log n has higher precedence over this one because n is polynomially greater than n log 3 by 4. N is 1, and this is like 3 by 4, always less than n. So this one has dominance, and we say that the runtime for this algorithm is n log n. This case is a bit tricky. You can see that the a here is 2, b is also 2, and fn, just like the previous case, is n log n. Here, when we apply transformation, n log 2 by 2, it's n, and this side it's n log n. Although n log n is always greater than n, but Master Theorem states that for a condition to be true, case 1, case 2, case 3, these two sides either have to be greater, equal, or less than in terms of polynomial. So although n and n cancels out, but this side, it's not polynomially greater than this side. Hence we cannot apply Master Theorem. Hence if someone says that applying Master Theorem log n is the answer for this algorithm, he's wrong, is correct, is incorrect. This is not the answer. This question cannot be solved using Master Theorem. You have to apply other techniques to solve this question. Alright, I'm presenting two more examples. Although they are redundant, we have done similar questions in the before, but I'm giving you two more examples for more clarity about Master Theorem and how to apply it. So in this question, let's start with this one. A is 2, B is 2, AB. Fn is a function of n to the power 1. So converting this one into n log AB structure, it's n log 2, which is n. And this one is equal to n over here, which means we'll apply the second case of Master Theorem, which is n log AB ln n. That is nothing else but theta of n1 log AB into ln n, which is theta n log n. So this is theta of n log n. And coming here, A is 8, B is 2, A and B. And n log AB is n log A2, which is n log 2 by 2, 3 over here, this 3 comes here, it's n cube. So n cube has precedence over Fn, which is just n squared. So we say that this algorithm is n cube, means that this side has the dominance. Friends, with these two examples, we come to the end of this really short lecture on Master Theorem and its applications. In the subsequent lecture, I'll give you the proof of Master Theorem. I highly recommend you guys to at least look at the proof at least once in your course, because that will give you the actual intuition of why this one works or why this one fails, or why we say like precedence is over towards the division or per step computation. So I will highly recommend you guys to look at that tutorial, because that's the difference between someone who can impress an interviewer at companies like Facebook, Google, or Amazon, and who is unable to impress the person. Anyone can solve these questions easily in any interview scenario and get the credit. But if you can get the intuition behind why these things work, that will make the difference. Thank you so much, and hope to see you in the next video.